To operate in space, humans must carry a precisely controlled atmosphere into an absolute vacuum. Containing that gas is the primary constraint of every mission. When containment fails, the threat takes two forms. A hypervelocity impact punctures the hull, and internal gas violently vents into the vacuum. This is rapid decompression. It is a mechanical failure, driven by the thermodynamics and fluid dynamics of gas escaping through an orifice. The second failure mode occurs entirely inside the human body. During a slow drop in ambient pressure, gases dissolved in human tissue bubble out of solution. This is slow decompression, a biological kinetic failure. Engineering a survivable space cabin requires solving both of these time-dependent opposing threats at the exact same time. Before engineers can model how a cabin loses pressure, they have to establish the chemical baseline required to keep a crew conscious and functional. The atmosphere's total pressure must be balanced against the concentration of oxygen to maintain a continuous, adequate partial pressure of oxygen in the astronaut's lungs. This chart defines the survivable environment. The clear section maps pressure and oxygen combinations, allowing unimpaired performance. The bottom line shows, as total pressure drops, oxygen must increase to prevent hypoxia. The top hatched zones dictate upper limits to prevent toxicity and narcosis. Any engineered spacecraft environment and any pressure transition the crew makes must remain inside this specific physiological envelope. Operating in space requires transitioning between different pressure environments, exposing the crew to dynamic physiological risks. During normal operations, human body fluids reach a saturation equilibrium with the partial pressures of the inert gases used in the cabin. If ambient pressure drops slowly, those inert gases come out of solution. They rapidly coalesce into expanding microbubbles within the tissues and bloodstream. These trapped bubbles cause decompression sickness. They lodge in the joints to cause the bends, block pulmonary vessels to cause the chokes, and can eventually trigger neurocirculatory collapse. This graph tracks new symptoms across a population following a pressure drop. The onset peaks tightly between 20 and 60 minutes. Plotted cumulatively, it forms an ogive curve. After 2 hours, the symptom rate flattens completely. Decompression sickness operates as a highly predictable fluid dynamic event, entirely governed by the equilibrium levels of the inert gas. That baseline mathematical curve changes drastically when external variables are introduced, specifically physical exertion. Muscular work creates localized pressure drops and agitation in the tissue, accelerating the rate at which gas bubbles liberate from solution. This graph compares cumulative decompression sickness rates based on movement. The bottom line shows subjects at rest. The top line shows a severe, rapid spike in symptoms for subjects performing deep knee bends. Because of this, a cabin operating at 7 psia with 50% inert gas is mathematically more hazardous during decompression than a 5 psia cabin with only 30% inert gas, simply because there is more gas dissolved in the crew's tissue. Since extravehicular activity demands heavy physical exertion in a low-pressure suit, manipulating the cabin pressure isn't enough to protect the crew. A preemptive countermeasure has to be taken. To mitigate the kinetic threat, crews undergo denitrogenation, routinely referred to as pre-oxygenation. By breathing 100% oxygen, the astronaut alters the partial pressure gradient in their lungs. This physically forces the dissolved nitrogen to diffuse out of their tissues and into the exhaled breath. The rate of this nitrogen elimination is plotted using a multi-compartment exponential decay model. The equation uses multiple time constants because nitrogen leaves different parts of the body at different rates. Blood clears rapidly, while fat stores hold on to inert gases much longer. This compilation of data shows how individual factors like age and physical conditioning create a wide spread in how fast an astronaut achieves protection, indicated by the varying slopes of these decay curves. Engineers must translate these theoretical decay models into strict operational timelines for the crew to follow. The protocol is rigid. Even a brief interruption with air breathing forces a recalculation of the decay equation and significantly delays the mission. Mitigating the threat of slow decompression requires hours of mathematical modeling and strict pre-breathing, placing a massive tax on the crew's schedule. While decompression sickness represents a slow, biological timeline of failure, A structural puncture introduces an immediate mechanical threat. If the hull is breached, survival relies entirely on the flow rate of internal cabin gas escaping into the vacuum. The time of useful consciousness during a blowout is calculated using the orifice coefficient and the ratio of the hole's area to the total volume of the cabin. But that calculation is highly sensitive to the thermodynamic nature of the expanding gas. These charts compare two flow models for identical gas mixtures, isothermal flow on the left and isentropic flow on the right. Mapping a half-inch puncture across both reveals a significant discrepancy in the calculated time to reach the minimum tolerable pressure. Depending on which thermodynamic expansion occurs, an astronaut might have 6 minutes to don an emergency suit, or they might only have 2. Surviving an explosive blowout requires calculating the exact mechanical limits of escaping gas, leaving zero margin for biological error. When you set the slow biological threat against the rapid mechanical threat, the central paradox of spacecraft atmospheric design emerges. A high-pressure mixed gas cabin contains more overall gas volume. In a blowout, it takes longer to vent, giving the crew a wider buffer of useful consciousness. But that same inert gas maximizes the risk of decompression sickness. Conversely, operating at low pressure with 100% oxygen completely eliminates the bends and the need for pre-breathing. But a puncture will deplete the cabin almost instantly, while introducing severe fire risks. Adding inert diluents buys crucial mechanical time during a blowout, but it creates a biological liability that drains hours of mission time before any extravehicular activity. Because these two kinetic models are inversely opposed, there is no perfect cabin atmosphere. Engineers calculate a strict compromise based on the exact risk profile of the mission. Atmospheric design is simultaneously a physiological and a thermodynamic discipline. Human tissue stores and releases inert gases at rates that cannot be bypassed. Sonic fluid flow through a ruptured hull follows physical laws that cannot be negotiated. These two kinetic realities dictate every operational constraint, timeline, and emergency protocol in orbit. Sustaining life in a vacuum is a continuous, multidimensional calculation of kinetic forces. Human survival depends entirely on the ability to mathematically model how fluid dynamics govern both the blood in our veins and the atmosphere in our cabins.